Hey, thank you for coming back to watch the chapter 4 extension number 2 video. Today we're going to be showing you how to interpret and sketch these graphs. So I gave you an example here where I talk about me taking a stroll in the neighborhood on an early Saturday morning. And it shows the distance in blocks that I am away from home as a function of time, meaning as I move and progress along time, as the time moves on, the vertical axis shows how far I'm away from, I guess, home. So I want to look at the graph, okay, see time is measured in hours. Here's 0.5, here's 1 hour, here's 1.5 hours. Okay, notice that this is the blocks from home, 1 to 10. So understanding this graph, can you actually answer these questions? How much time did it take to complete the total trip? So I guess total trip would mean leaving home and coming back home. Yeah, you'd be starting here and ending at 1.5 hours. 1.5 hours. Now, my next question is, how much time was I stationary? So how long during this 1.5 hour journey was I actually not moving, just stopping? So if you think about stopping, that's the time when you actually didn't change the number of blocks. So that would be the horizontal distances here. Since each one of these is, 10 minutes, I think? 10, 20, 30 minutes, so 30 minutes or half an hour. Now, what is the domain? The domain, of course, is the number or the elements in the independent variable. The independent variable in this case is time. So if you want me to write it properly, this is actually how you would do it. You can say time is actually bigger or equal to 0, because it's starting at 0, and it also ends at 1.5 hours, 1.5 hours. Okay, and what does the domain represent? It represents what? The time the journey took, but of course our units are in hours. Okay, now what about the range? The range in this case goes from 0 all the way to the highest value, which is 9. And what does this represent? Maybe this represents the distance from home, measured, of course, in blocks. Don't know how long these blocks are, but they seem pretty long. And if the question says in part E, how far did I go away from home? So think about, as I traveled along here, how far did I go? It looks like I reached the maximum here of 9 blocks. So I went 9 blocks away from home, and then I guess I came back home. Now here's an interesting question. During what times was Mr. Lee walking the fastest? So walking the fastest means covering the most distance in the shortest amount of time. So how do we calculate that? If you thought about that as this piece here, really steep, I agree. This one here, also really steep, I totally agree. So during what times? Well, it was between, I guess, that would be the first, first 10 minutes, I think. So maybe the first 10 minutes. Remember, if this is 1 hour, then 1, 2, 3, 4, 5, 6 times 10 is 60 minutes. So for the first 10 minutes, and also the last 10 minutes, that's when I was walking the fastest. Okay. Alright. So, now the last thing is this interpreting. Can you actually put a story to the journey? Can you show me actually what happened and write a little, story about what was going on? So I'll tell you actually what happened. So from 0 to 10 minutes, okay? I went with my kids, Mr. Lee. With the kids, went to the park. And we were running pretty fast because my kids were excited, so yeah, we went to the park. And so what happened at 10-20 minutes? Well, yeah, we started arriving at the park. We arrived at the park. And then what happened? And of course, the kids played. Yes, I let them play for 10 minutes only. So why did I only let them play for 10 minutes? Well, because from 20 to 40, they were getting hungry. And so I said, okay, let's go and then walk to the ice cream store. So we walked to the ice cream store. And then guess what happened at that point? By the way, the ice cream store was probably the farthest away from home, right? 9 blocks away from home. So from, in this case, 40 to 50 minutes, do you know what happened? Yeah, we were in the ice cream store choosing the flavors. And of course, after 10 minutes, then guess what? We got this ice cream. We're eating it. It's gonna like melt, so we better walk back home. So from 50 to 70 minutes, we actually start to walk back home. We start to walk back home. And then, hey, the kids see the park again. So guess what they want to do? Yeah, they want to play at the park. Kids stop to play at the same park. And of course, I only let them play for 10 minutes. Why? Guess what happened? After that, from 80 to 90, we had to go home. Why did we have to quickly go home? Mom called. Mom called to tell us to get home fast. So we ran home. And so I came up with this story to actually describe what happened to the graph. And this is what we need to do. We need to be able to interpret the graph, which is the part above, and also come up with a situation. So in example number 2 now, I want to give you a situation. I want you to actually draw the graph. So it says draw a sketch or a graph of showing the temperature in Burnaby on a given winter day now. Okay, winter day. So be sure to label your graph. So on a winter day, I guess we have time, right? Hours. And then I guess we get 0, I don't know, let's say 6 hours or 6 a.m. perhaps. We'll say 12 noon. Maybe 6 p.m. and then maybe 12 midnight, right? And what would be on my dependent axis here? Yeah, the temperature. Good. Temperature. So maybe on a winter day, maybe it'd be negative, I don't know, negative 4. 1, 2, 3, 4, 5, 6, 7, 8 degrees Celsius. Okay. So if you think about what happens, yeah, maybe at nighttime it's like -1, but as it gets lower and lower, it gets lower. But then guess what happens around 6 o'clock? Maybe it's getting warmer. Maybe sometimes it gets warmer, and then maybe it actually gets really warm, like above the freezing level. But it probably didn't go that far or that high. Maybe at 6 o'clock it's coming back down, and then maybe at midnight it's back. Say something like that, like here. So something like this, and by the way, you don't have to draw something like this. Maybe your graph looks more like this. I don't know. It's up to you. But as long as you can draw something out and then describe it, that's what I want you to do. Okay. Now, just to let you know, there are some properties that the graph can provide. If I was talking about distance and time, kind of like the one from above, okay, this part here is what I call a steep increase. And this is a steep decrease. And when nothing changes, it's flat. Okay? A moderate increase, a very steep decrease, and a moderate decrease. So just being able to see how the different, I guess, steepness of the line might affect your graphs. Okay. Alright, the last one here. I've got an example where I want you to look at this information. This is real information, by the way. There is an actual frog jumping competition that happens in Manitoba every single year. And the first champion ever was a frog named George. and he jumped a distance of 2 meters in a single leap. Yeah, 2 meters. Social distance, right? He knew how to do that way back then. Assuming that yours could maintain a distance of 2 meters on every jump, and that the total distance traveled from the start is measured after every jump, I want you to investigate the relationship between the number of jumps and the total distance that he traveled from the start. So if I ask you to make a table of values, what am I actually trying to graph out here? Well, I'm saying give the relationship between the number of jumps with the total distance. 0 jumps, of course, no distance. 1 jump, 2 meters. 2 jumps, 4, 3, 6, 4, 8, 5, 10. You're like, easy. Fair enough. So, part B says, determine which axis is for each variable in state Y. So, the horizontal axis is always the independent variable. And our independent variable in this case is, the number of jumps. Right? The frog gets to choose that. Our vertical one always represents the dependent. And what would that be in this case? The total distance. So, let's go ahead and sketch that. Ooh, that's not a very straight line. Hopefully you do a better job of your notes than mine. Number of jumps. 1, 2, 3, 4, 5, 6. And then here I'll have 2, 4, 6, 8, 10, 12 total distance. And distance is measured in this case, meters. So I can plot the points, right? 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10, 6, 12, and so on. So my next question to you is, should these data points be joined by a line? So should I actually connect them together like a line? And the answer in this case, once again, is, or not once again, but is, no. Why not? Really? If you join a line, you're saying a frog can jump 1.5 times? Or 1 1/3 times? Like, can that really happen? So, a frog can only jump whole numbers. Okay. Last time I checked, a frog can't be jumping 1.5 times, or 1.2375 times. Okay, so therefore, because you're not including decimals, since decimals not included, don't join points with a line. Okay. Now my next question is the relationship between the number of jumps and the total distance a function? Do you remember what we talked about with function in the last video? A function, once again, for each value of x, or independent variable, there's only, that's right, only one value of y, the dependent variable. And in this case, you bet it is, yes. Okay, so for each jump, there is only one total distance associated with it. Okay. And then for part F, would it make sense to actually extend the graph to the right? So would it make sense to keep going this way? I definitely think so. How about to the left? What happens there? Becomes negative? No. Can't jump negative distance. And remember, what is the domain and range of this function? Well, the domain, once again, is all the possible values of x, or the independent, and that's, of course, just all the whole numbers. So I'll say the number of jumps belongs to the set of whole numbers. Where for the range, I think we're looking at what? Every multiple of 2. So really it's every even number, or I'll say 2 times j, where of course j is once again a whole number. Okay? And so that's how you can describe domain and range. Now, one last thing here before we end today's video. Data that appears to be in a line. You see how these look like they're in a line? Yeah, I mean, we're not going to draw a line, but they look like they lie on a line. Do you know what they're called? Yeah, they're often called linear functions. And we'll talk more about that later on in our course. Okay? But that's it for now. You finished extension number 2.